Welcome back. In this video, we'll be going through the basics of simple linear regression, fitting a line to a bivariate data set. So as before, I have the list of learning objectives. We'll check in at the end, and you can verify that you hit all of these points. All right, so simple linear regression is something we can do with a bivariate data set. So we'll again, start with a scatter plot, but this time we'll be actually fitting a line to the data. And the equation of that line can help us predict values of the y variable based on inputs for the x variable, right? So simple linear regression is all about prediction. Now, unlike correlation, where in correlation, it didn't really matter which variable was x and which was y. They were treated equally. In linear regression, that distinction is very important because due to the nature of how the line is fit, we can only predict y. We cannot predict x. So x, there's a few different terms for this. Some people call it the independent variable, predictor variable, or explanatory variable. And y is usually called the dependent or the response variable. So our sample regression line is going to predict y. So you see the y here in the equation has a little hat on it. It also has a subscript I, indicating that that is the specific prediction associated with a particular value of x. All right, so when we plug in x here, we get a prediction for at that x, what do we expect y to be? All right, if you think back to Algebra 1 in high school or middle school, if your school was like mine, we learned that the equation for a line was y equals mx plus b. So it's like that here. They've just rearranged it a bit and used different letters. So the thing that gets multiplied by x, that's the slope. So the slope of our sample regression line is symbolized b1. And then the piece off by itself, that's the y-intercept. So the y-intercept of our sample regression line is b0. All right, so say we have a data set. I'm going to be using the gas stations data set that we saw in the correlation video. And here I have on the x-axis is the traffic volume. So I'm going to be using the traffic volume to try to predict the sales at a particular gas station. All right, so where exactly should the regression line be placed? Well, we're going to start with this restriction is that it's going to definitely pass through the point where the average x meets the average y. Okay, so imagine the star is a fixed point, and then we just have to figure out what slope to get the best fit. So to illustrate what makes a good fit, let's start by a counterexample. What would be a really bad fit? Okay, so we have a line here that does pass through that point of averages, but is clearly not doing a great job at capturing the trend in the data. All right, so let's show numerically why this is a bad fit. We're going to do that using the concept of residuals or errors, which we've seen before in the context of ANOVA. So generally speaking in statistics, the error is the actual response value, what actually was observed, what happened, minus what was predicted by our model. Okay, so the errors you saw before were in one-way ANOVA. So there, we took the actual value and subtracted the sample mean for the appropriate sample. The example there was with cars and how fast they could, or in what distance could they stop. So if we wanted to calculate the error of a particular car, we need to find out, well, how far did it take to stop, the actual value, and then we'd subtract the sample mean for that particular type of car, whether it was a Chevy Malibu or a Toyota Camry or whatever. Okay, well, with linear regression, where you're going to start, again, with the actual y value, but then we're going to subtract the y value predicted by the regression line. So I'm just going to substitute in on the right here what we saw on the previous slide, 2 slides ago, came from right here. So it was the predicted. Okay. So that difference will be the error. So let's look at, what would this look like graphically. So for every single gas station, and we have 80 of them, we could calculate, well, what was the actual sales? And then take from that, subtract out what was predicted by this regression line. And the height of the line represents the size of the prediction. So up here where the line is taller, we're predicting more sales. So let's say there's a gas station here. Looks like it has about, roughly 32,000 vehicles passing by. All right, so there, the actual sales, if we look how high is that point, it's a little under 8, like 7.8 or 7.9. So we'd have 7.8 or 7.9 minus, well, at that same x, so lined up vertically at x equals about 32, how high is the line? And here it looks like it's over 10, like 10.3 or so. So that number would go here. So that bolded line here, that segment represents the size of the error for this particular gas station. Now this particular gas station over here was only a little off the line, and it was a little above what was predicted. So that would be a positive error there. And then this huge error down here is that, well, this line is really bad fit. So the actual sales were way above what this line would predict at about x equals 50. All right, so if we wanted to measure on that whole, for this whole data set, how is the fit? One thing we might want to do is sum up the total amount of error. Right? We saw this in ANOVA. Well, some of these errors are negative, like this guy. Some are positive, like these two. And we don't want them to cancel out. So what would we do? We could square them before we add them up. And that would give us a sum of squares of the errors. Okay, now you would never want to do this by hand. I mean, the math isn't that hard, but here you would have to add up 80 parts. So JMP is going to do this for us. But rest assured, in this case, due to the really poor fit, we're going to get huge up here and down here. We're going to come up with a very large total sum of squares. All right. So our regression line, the one we're actually going to use, is called the least squares regression line because it's going to be the one that minimizes this sum of squares. All right. So we see the line going really through the cloud of points, and mathematically, what's ideal about this placement is if we calculated all the errors and then squared them and added them up, this configuration would give us the smallest total. All right, so it does a much better job. Some of the points look like they're right on the line. Many are just a little above or a little below, and it's only rarely now that we're too far off. Pardon me. All right, so to get this line to appear and JMP, I'm on my gas stations. We're going to use analyze fit y by x. And just be careful what you assign as x and what you assign as y. So we want to use the traffic, so that'll be x, to predict the sales. The thing you're predicting is always going to be y. All right, so that will make the scatter plot. And again, like last time, you want to confirm that there's no curved patterns before you proceed. And then I'm just going to use my drop-down menu and ask it to fit line. And we get lots of output. But for now, we're starting with the basics. We want to know what's the equation for that line, and it's down here, the first thing under linear fit. All right. So let's see how that equation can be put to use. All right, we said that the primary goal of linear regression is to predict. So there are some caveats. We can only predict values for y, as explained earlier. And now the reason should hopefully be easy to explain. It's because when we positioned the line, it was to minimize error for y. Our formula for errors only looks at y. It's not using x. So that's the reason we can't predict x. So we're going to predict y. So the way I have it set up, I can predict sales. And I can only do this within the observed range of x, which is to say, what traffic volumes were observed. Looks like the smallest is down around 25,000 vehicles. The largest is maybe at about 50 or so. So I can predict between x values of 25 and 50. But I shouldn't go beyond. So I shouldn't go higher than 50. I shouldn't go lower than 25. Those would be extrapolations. So extrapolations means, extra beyond the range of values for which we have data. Okay, so we don't know if this linear trend continues as x increases, or maybe it levels off at some point, or who knows, maybe even it curves downward. It's unknown to us, so we shouldn't go out there beyond the graph. All right, so have a look at these three questions. And for each, I want you to think about, is this a prediction that's appropriate to make? And if it's not appropriate, what's the specific reason why? Okay, so maybe pause the video here and answer those questions. All right, the first one. Can we predict the traffic volume when sales are 8,000 gallons? So sales of 8,000 gallons, well, that's being given Y and being asked to predict X. We can't do that. If we wanted to do that, we could maybe go to jump and fit Y by X and switch the roles, and then we'd have a different equation. We could use that equation, but not this one. Okay, so we can't do this first one because we can't predict X. All right, the second one, when the traffic volume is 40,000, can we make that prediction for sales? We're looking at the graph, 40,000, it's an X, and it's within the confines of the graph. So that's a prediction that we could make. The second one is good. And then lastly, predicting the sales when the traffic volume is 80. Well, traffic volume, so it is an X, but 80 would be off the graph. We don't know if the linear trend continues. So we shouldn't do the third one because it would be an extrapolation. All right, so let's actually make the prediction for the one that's allowable. So when the traffic volume is 40,000. Okay, so the equation here, I've just translated that into a little bit cleaner text. So we're predicting the sales, and then the first number, just the one by itself, that's the y-intercept. And I'm going to round here to 3 decimal places. So the y-intercept is negative 1.338, and then it's plus, and then the number that gets multiplied by x. So the thing multiplied by traffic here is numerically about 0.237. So that's the sample slope. And that slope will multiply by the traffic volume that we want to use to make the prediction. So we're going to multiply it by 40 because that's the number of thousands of vehicles we're interested in. Now, just a little note, since my spreadsheet has them already in thousands, like notice here, we've got a 40. I'm not going to plug in 40,000 to this equation. It's set up to do it already divided by 1,000. So just pay attention to the formatting of your data table and make sure it is on the same order of magnitude there. Okay, so multiply the slope by 40 and then subtract out this intercept here. And the predicted sales would be 8.142 thousand gallons of gasoline. So at x equals 40, the height of the line, that is, should be 8.142. and jump. So at 40, if we go up, how high is it? It should be at 8.142. Now, I will want you to use the equation to come up with your predictions. Usually you can eyeball it based on the graph, but this is stat 2. We want a precise answer. All right, so as I just pointed out, there actually was a gas station. It's in row number 63, who did have 40,000 vehicles passing by. And it turns out they actually sold 8.84 thousand gallons. So this is the actual Y value. So if we have the actual X and the actual Y, and we have the equation for the regression line, we can calculate the error associated with this measurement. So the formula for error, remember, kind of generally speaking, is actual minus predicted. So the actual was that, according to the data table, this station actually sold 8.84 thousand. So that goes first. And then we're going to subtract out what would be predicted by our regression line for that given X. So if X equals 40, what comes out of that line? So this is what we just solved for on the previous slide. So we subtract, and I've labeled this E63 because this is the error associated with the gas station number 63. It's in row 63. All right, so that error is, in this case, positive 0.698. So what does that mean? Well, remember, the errors are the vertical distance between a point and the line. So vertically meaning at that fixed value of X. Here, X equals 40. So looking at the scatter plot, we see this is gas station number 63 in black. The rest are all in gray. And it is above the line, and it's 0.698 above the line. Now, in context, remember, this is in a measurement or error in terms of Y. So Y here was the sales in thousands of gallons. So this is how many thousands of gallons that gas station number 63 exceeded the expectation by. Our regression line equation predicted that it should sell 8.142. But it actually sold 8.84. So it outperformed the expectation by this amount. So it's 0.698 thousand gallons. And to make it, very straightforward to interpret, if you multiply by 1,000, that would be, it sold 698,000 gallons more than we predicted. Now, if you had a negative residual, that would be represented by one of these points that's below the regression line. So in that case, these gas stations down here underperformed. They did not sell as much as we would have expected based on their traffic. All right. Let's now think about the numbers in our equation and what they represent. So let's focus on the slope for a moment. So the slope, remember, is the number that gets multiplied by X. So this is really the lever, if you will. This relates, changes in X to changes in Y. And we can think about, say the traffic goes up by 1. Well, we'd have 1 times 0.237. So this is the change associated with a 1 unit increase in X. And that's true for any regression line. As X increases by 1, how much do we predict Y will either increase or decrease? So if it's a positive slope, a plus sign, we predict an increase, and the number would tell you how much. Whereas if it was a minus sign here, it would be a negative slope, and that would tell you how much of a decrease we predict. All right, so here is a kind of fill-in-the-blank interpretation you're welcome to use. So if we adapt that to the sales regression line equation, we could say for each additional 1,000 vehicles passing by, because X was in thousands of vehicles, we'd predict here an increase, because it's a plus, an increase of 0.237 thousand gallons of gas. Now, I say 0.237 thousand gallons of gas because this will give you a template that's easy to follow. If we really wanted to make this as clear as day to interpret, I'd probably go ahead and multiply, and then we could say 237 gallons. Right, my slide is a little out of turn. So I want you to go ahead and open up the muscle data set, fit y by x, and add the least squares regression line, and then go ahead and interpret the slope that you get. Right, so pause the video here and go ahead and do that. All right, so here's what you should have got. Now notice the trend here is negative. We saw that as age increases, the lean muscle mass tends to decrease. Now, jump was a little sinister here. It has a slope, the number for the slope down on the second line for me, but the minus sign was broken up and put on the first line. Okay, so always just do a quick check and pay attention to the pattern on the scatter plot and make sure your answer makes sense. All right, so here, X is age. So for each one additional year of age, we predict, what do we predict? We predict a decrease of this amount, a decrease of about 1.02 pounds of lean muscle mass. Okay, so it's the rate of change, for at least this demographic of middle-aged and elderly men. We expect that for each year older, they'll lose about 1.02 pounds of muscle. All right, so the y-intercept, that is, in the algebraic sense, what we get if x equals 0. So say here, if traffic was 0, this term would drop out of the equation, and we'd be left with just the y-intercept. So that is, if we were to zoom out on our scatter plot, what's the height of the line when x equals 0? Now, it would be tempting to interpret this as the predicted sales when x equals 0, but we shouldn't do that because it is an extrapolation. And also, it wouldn't make sense that they'd have a negative amount of sales. All right, so if x equals 0 is an extrapolation, then we'll just simply say that, well, this value, negative 1.338, would be the height of the regression line when x equals 0. Similarly, for the muscle mass, x equals 0 is an extrapolation. We certainly wouldn't expect for a newborn baby to have a lean muscle mass of 148 pounds. So we would just say there that when x equals 0, the height of the regression line is about 148. But here's an example where interpreting the y-intercept is actually something that's reasonable to do. So this was my fictional data set from the correlation video where we're relating the number of hours a student studies to their score on an exam. So here, 0 is not an extrapolation. There was actually someone who studied for 0 hours. So the height of the line when x equals 0 is this intercept, 47.2. But we can go a little further this time. Because it's not an extrapolation, we can put it in context and say, for a student who doesn't study at all, we predict that their score would be 47.2 points. Now, this is actually a quick and easy residual we calculate. For someone who doesn't study, we'd predict that they would score 47.2 points. We actually did have someone who did not study, and they scored 46. So remember, you take the actual y, 46, minus the predicted y, 47.2, and this one would be negative 1.2. So looking at the scatter plot, this student here who didn't study at all, they got a low score, And in fact, slightly lower, 1.2 points lower than we would have predicted just knowing that they hadn't studied. All right, so that is the end of the video. Go ahead and read through the learning objectives. Make sure you are familiar with all of them. And I will see you in the next video, which is on measuring the fit of the line.